Welcome to Excel 2013 Statistical Analysis video number 48. If you want to download this workbook, Business 210 Chapter 8, or the PDFs for Chapter 8, click on the link below the video. Hey, we're in Chapter 8. We're going to talk about how to construct confidence intervals. Now, here are our four main topics that we'll cover. But before we jump into Chapter 8, I want to jump over to the PDFs and compare what we did in Chapter 7 and Chapter 8. Now, the PDF start at page 1, but I have 2 pages before that that don't have a page number. So let's remind ourselves of what we did in Chapter 7. First main point we did in Chapter 7 is we knew what the population mean mu was, or we had a good estimate of it. So we, in our insurance cost example, so annual cost, we knew that the population mean was $822. We then added a margin of error and subtracted a margin of error to get a lower and an upper limit. We then made statements based on a 95% probability. We said the probability of getting an Xbar between 799 and 845 is 95%. That allowed us to take a sample and compare our sample to the sampling distribution of Xbar. So we get, if we went out and got a sample of $837, well, that lies within this range here. So we assume that the original claim is reasonable. In essence, we say, well, 837, that's just sampling error. So we'll assume that the original value seems reasonable. However, if we got a value out here or down here, for example, if we got an Xbar equals to $850, well, then the sampling error, the distance between these two, is so big, we then say, well, maybe this original claim is not reasonable. Now, very clear, this, and I have it written down here, the statements we made in Chapter 7 are, we believe that 95% of the Xbars will lie between these two values. Chapter 7, we knew, or had a good estimate of population mean. Next page. But what do we do if we don't? So we just flat out don't have a good way of estimating this. Well, then we go out and we take a sample. We add margin of error to either side to get what's called a confidence interval. And at 95%, we say we're 95% sure that the population mu lies in our interval. Now notice something here. There's our Xbar of $837, but we're not directly comparing it to our sampling distribution of Xbar. However, we are going to use the same techniques, Excel techniques and probability techniques, that we learned in Chapter 7. It's just we can imagine that there was a bell-shaped curve over here, and we'll use all the same techniques. But technically, we're not measuring it up against this sampling distribution because we just don't know what mu is. Now, if we go back to this previous page here, see our Xbar, we were comparing it right up here because we knew mu. That page right here. All right, let's go to our next page here. So in Chapter 8, we don't know what the population mean mu is. Now let's look at another example, printer cartridge manufacturer example that'll help us kind of think of situations when we really can never calculate mu, and thus we have to learn how to create confidence intervals. All right. When printer cartridge manufacturer wants an average number of pages per cartridge. Now think about this right here. Your manufacturer of printer cartridge is going to run an ad, and you want to say something in the ad like the average number of pages you can expect is, or on the back of the box, right, that you delivered. It's got to say what the average expected pages are. Well, you can't know mu, right? And the reason why is you can't calculate the population mean because they can't go out and print all the pages for all the cartridges, right? So that's where confidence intervals come in. So we're still going to use point estimates. So we'll go out and take a sample. We'll get 2,409 pages. That's the average from our sample, or the mean from our sample of number of pages. But we can't use this, or we can't compare it directly to the sampling distribution of Xbar. So what do? We're going to add a margin of error to our point estimate. And we'll do this example a couple of videos ahead. We'll get a margin of error of 217 pages. So we'll create a 95% confidence interval that says we're 95% sure that the population mean lies between 2,190 and 2,620. So you might even see in the ad or on the back of the book or the manual that comes with the printer cartridge, it would say something like 2,400 pages with a margin of error of 200 pages. Now, the statements we can make in Chapter 8, again, we are 95% sure that mu will lie between the two limits. Back in Chapter 7, we were comparing Xbar. Now, 95% sure that mu will lie in our interval here, right? Let's talk a little bit more about that 95%. We'll go to the next page. For 95% confidence intervals, because we don't know the mu, technically it would look like this. Sometimes our interval would contain mu, right? We don't know this. Mu, here's the sampling distribution of Xbar up here. But down here, we calculate based on our sample mean, our interval. But notice this one theoretically contains this one. This one contains the mu. So does this one. But this one does not. So this just flat out, we calculated our sample mean, added our margin of error, and then we say we're 95% sure that our population mean lies with this interval. But it's the 5% risk that it doesn't lie in this interval that's illustrated here. So if you were to create 100 similar intervals, 95 would contain the population mu and 5 would not. Now, this analysis here assumes that the original population distribution is normal or bell-shaped or near normal or bell-shaped. If it's not, then as long as you have a big enough n from the central limit theorem, then about 95 intervals would have the population mean and 5 would not. All right, next slide. Let's notice something for the printer cartridge example. And we already mentioned this. We cannot calculate population mean. Why? Because we do not have we can't possibly test every cartridge made or count every page for every cartridge in every house. Not possible. In this case, we do sampling and create a confidence interval. Other examples, we do not know how many meals married couples eat out each week. There's no way to calculate that. No database you can go to get that, all that data. We do not know what the mean amount of profit is per auto sold in the US. So 3 examples here included in our cartridge example where confidence intervals is a great way to estimate the population mu. Here's our formal definition of confidence interval, an estimate of the population parameter that provides an interval believed to contain the value of the parameter. Right? Our formula in the general form will be this: point estimate plus or minus a margin of error. So for Xbar, we'll have calculate our Xbar plus or minus, and we'll learn how to calculate the margin of error in just a moment. Now, we've been talking about 90%, 95, 99% confidence interval. So the confidence level or confidence coefficient, this textbook says confidence coefficient. I tend to say confidence level. That's probability that your population parameter is in the interval. So 90, 95, 99. Now, that other little bit of probability, 10, 5, 1, is called level significance or alpha. And that's the risk or the probability that the interval does not contain the population parameter. Our next slide will show our official formula that we'll use. Number 6 on the page, number 8, I think, in the counter down at the bottom of the PDF. Here's our confidence interval for mu. Now, we're going to have 2 of these formulas. And deciding which formula to use depends on sigma. Sigma is the population standard deviation. If you know it or you have a good estimate, which is not usually the case, then you use the z distribution in our formula. Now, sigma known, sometimes you have a lot of population data amassed, so you can calculate or have a good estimate. Or in quality control calculations, sometimes it's safe to assume that you know sigma. So for some cases where we know sigma or it's a good estimate, we can use z. in a couple videos ahead, we'll see how to use a new distribution called T, which is the more common usage because you oftentimes don't know mu or sigma. But confidence interval when you're for calculating an interval for mu when sigma known. All right, here's our formula. Here's our variables. Now, x bar plus or minus, that whole thing is the margin of error. Now, this little part right here we've seen before, that's standard error, right? Sigma divided by the square root of n. That's the standard deviation of the sampling distribution of x bar times, and what's z? Z is number of standard deviations. Now, we'll talk about this alpha divided by 2 in just a moment. But z we've dealt with a lot so far in this class. So it's z times the standard deviation for the sampling distribution x bar. Now, what's this alpha divided by 2? Let's go back a bunch of slides. I think all the way to go to 1. No, sorry, 2. Now, here's our picture. This is our sampling distribution of x bar. And again, we're not comparing when we're doing confidence interval directly to this, but all the same math works. So watch this. If we're talking about 95%, the alpha or the risk is 5%. Well, half of it has to be there, and half of it has to be here. So alpha divided by 2 is that little bit right at the top. So when we say z of alpha divided by 2, we mean z on the upper end. Notice because the distribution is symmetric, if you have z on the upper end, you just slap a minus sign in front of it for the z on the lower end. All right, I don't remember which slide we were on. Oh, there it is. All right, so that's z on the upper end. There's all the definition. Notice they define confidence level as 1 minus alpha. That's because alpha is the risk, mu not in the interval. So usually you think about your risk up front, and then you take 1 minus that to get your confidence level. That means how sure you are that the population parameters within your interval. Now, in our next video, we'll calculate all of these and see Excel. We're going to have method 1, 2, and 3. Norm.inverse function we've already used a bunch. We are actually going to be able to calculate the upper limit and the lower limit directly using the norm.inverse. Now, in the textbook, they don't show you this. They show you this method 2 and 3. But I'm going to show you this just because if we've already been using these, and we can use these to calculate an upper and lower limit. Method 2, calculate the z upper. We saw this one earlier also. Norm.s.inverse. That gives you that z. And then you already have the data for calculating this, so you multiply those together, and that's the margin of error. So method 1, 2. And method 3, here's a brand new function called confidence.norm. A couple videos ahead, we'll learn about the t-distribution, and it will be called confidence.t. But confidence.norm means z distribution. Now notice, here we're going to have to calculate, for the norm.inverse, we're going to have to calculate the standard error. For the norm.s.inverse, all we need is the probability from negative infinity up to alpha divided by 2. But notice this. We don't have to make many calculations. We have alpha. Since sigma is known, we're given that, and we have the sample size, you just plug these in, and confidence.norm, because it's got sigma and n, will calculate the standard error. And alpha, obviously, can divide by 2 and do all that. So this function's real nice because you can quickly get what's the margin of error. And that's directly the amount added and subtracted from your sample mean. All right, so in our next video, we'll finally get down to some calculating. We'll use all the data from this page here. All right, see you next video.